Hello and welcome to Deep Learning with Pytorch, Lesson 10. Now we're in Chapter 6 here, which is using a neural network to fit data. We're going to be doing the same thing that we did in Chapter 5 with the Fahrenheit to Celsius conversion, just a linear relationship data set. Obviously, you could just use a linear model to fit it, as we did. Linear regression would work very easily, but we're showing this on a simple problem, and now we're showing that same simple problem with neural networks, so that we get a full understanding of how neural networks work. So if we go here, we can see the learning process for a neural network. We have some sort of inputs, we feed that in, and all of these weights are updated. A loss function is calibrated, and then an optimization function. So loss is determined, and then optimization is applied based on the loss function. And remember, loss function has to do with gradients and all of that. Optimization function, we haven't really learned the inner workings of Atom, but there's different optimization functions. We saw that before. And it will continue to iterate until the weights in this the weights in these different layers are adequately tuned so that our inputs will give our desired outputs, our ground truth. So before, we just had basically a y equals mx plus b, so the only weights we were changing was the m, if you remember. We had a bias and a weight. The weight we were changing was just one weight. The thing about a neural network composed of many layers, and each layer being maybe 10 nodes, 20 nodes, is that these can organize into different ways to get you to your desired output. So that it's not just one configuration. There are many configurations that could lead to a desired output. And one of the main things with neural networks, I always forget what this theorem is called, neural network theorem. Universal approximation theorem. So what this basically states, the universal approximation theorem, is that a neural network can be used to artificially model any function. So that's a very bold claim. In mathematical theory of artificial neural networks, universal approximation theory, I don't know if they just have a one-sentence definition. Universal approximation theorems imply that neural networks can represent a wide variety of functions when given appropriate weights. On the other hand, they typically do not provide construction for the weights, but merely state such a construction is possible. Okay. So with physics, that's what we do, right? We model behavior and we come up with equations, and that's what Einstein did. That's what Newton did. Newton came up with these laws. He exploited calculus to come up with these laws of gravity, or his 3 laws of motion or whatever. And we're just taking equations and fitting behavior. Neural networks do that, but the only issue with it is that it's treated as a black box. We don't know what is inside of this. We don't know why it arranged the weights in the manner that it did. We just know that using this training process, we can train this input to equal that output. So we go a little bit further. This is what each neuron looks like, each node inside the neural network. If we look at a neural network, just not theorem, we'll just say an image, just real quick, and we go to an image here, that's a neuron right there. I mean, hopefully we already knew that, but here's an input, here's our output, these are neurons. So at each neuron, this equation is taking place, which is basically just 3 things, and they're all very easy to comprehend. Learned parameter, that's our weight, W. Our input is X, that's all of the inputs. It could be summed up from all of the previous nodes. And B is the bias, so we're adding that. And this is a linear transformation. Here we have a non-linear transformation. This is a hyperbolic tangent, and this will all equate to some given output. So let's say that here's our inputs here, 18, negative 2.75, and negative 10. These are all coming in. These are all the values from our previous node getting fed. So here's a node. It's getting 18, 2.75, and this, all from the previous node. So it does this calculation. 2 is our W, and 6 is our bias. So we're just doing a very simple algebraic formula here. And then after that, we're going to take this 42 and feed it into the tan hyperbolic. Now, you might not remember what tan hyperbolic does, or maybe you've never heard of it before, but these are just simple activation functions, and I believe there's more listed down here. I'm skipping kind of far ahead, but here's hyperbolic tangent, here's hard tan, here's the sigmoid, soft plus, ReLU, leaky ReLU, and we basically have a set of values that we feed in to it. Let's go back up. So 42, all of these values get fed into our hyperbolic tangent. Why do that? Why not just leave it as 42 and all of this? Well, what it does is it rescales it. So we have this wide range of values, and it will squish it all down to somewhere between -1 and 1. So this one is 1 because it's so high. This one's -1, and this one is 0.3969. The hyperbolic tangent is one we see a lot. We also see the sigmoid because that gives us a similar pattern where it will all go out into somewhere between 1 and 0. You could think of it also as a probabilistic value because it's between 1 and 0, or -1 and 0. So there are many benefits to doing that. It's kind of like scaling. But none of the mathematics on the inside of this engine are overly complicated. Like, you could learn how to do this. You can plug that into a calculator. You can do all of this on a calculator. Very simple, and understand it. You may not be familiar with seeing all of these nonlinear functions, but they're not complicated. Look at the shape of it, plug a few numbers in it, learn the behavior, and that's all you really need to do. And you don't really even need to do that from a macro perspective when we're tuning these neural networks. So here we have some more stuff. We're seeing the full layer by layer of the neural network, and it's just kind of breaking it down into 2 steps because in the blue we have this learned behavior, and we're calling that a learned behavior. It's really just the linear activation, linear transformation, the W times X plus B. And then we take that learned behavior and we take all the values we get from that and put it into our nonlinear activation function. And we do that at every layer. And we can customize these, so we can make them however we want. We don't have to do the nonlinear activation function at every layer, but that does help us to model nonlinear behavior. So what about the data we're modeling right now, or going to model in this lesson? We're talking about a linear behavior, right? Celsius to Fahrenheit, that's a linear relationship. We could do that with just using the linear transformations. However, in most cases, when you're using neural networks, you're modeling a behavior which is very complex. Therefore, you would want to use the nonlinear activation functions in order to model that complex behavior. I think that's just about all. I forget what this one is saying. Here we have the sigmoid, which a sigmoid is just 1 over 1 plus e to the negative x. So that's 1 over 1 plus e raised to the power of negative x. Here's the function here. So no matter how good, what we're modeling here is a function that predicts if an image is a dog. So the garbage truck, it's like, that's definitely not a dog. It got a result of -42 on the linear transformation. We apply that -42 into the nonlinear transformation. Anything down here is going to go to -1. Any value, -1. So no matter how bad it gets, it can ultimately get a value of -1, which is basically, you could consider it like this is 100% chance that it is not a dog. And this one, the best value it could get is a 1, which would be like 100% chance that it is a dog. And then this grizzly bear here gets a value of 0, or somewhere in the, they say, in the -0.3 to positive 0.3 range. So it's just like maybe it could be a dog. We're not very sure. Very much dogs, definitely not dogs. So that's why we apply this linear transformation, to get some form of a probabilistic output. Here are the functions. We'll go through this really quick. There are 3 sets of code in chapter 6. We'll go through each one. We'll start with 2 because it's just the activation functions. It's not even listed in the book, but we'll just run through it real quick. Let's import all. Let's restart clear our output. Typical stuff we're seeing here. Importing our various modules that we need in order to run this code. Boom. We're importing Optum and in as well here. That's something kind of new. All right, now we're going to set up a range. So what we're going from here is from -3 to 3.1 in intervals of 0.1. So we'll print that out because we have that written here. So it's going to print it. And there we see it. -3, -2.9, -2.8, so on and so forth, all the way to 3. You can see that's why they wrote 3.1, because obviously it doesn't include that 0.1. It stops 1 before that. If we just did 3, we would end at 2.9. They were like, no, we don't want that. We want it to 3. Okay, fine. Now we're going to print out an activation list. So all the complexities that you might have seen with those nonlinear activation functions are not that complex from a coding perspective. We're just calling it from the in module, torch.in. So here we can call any of those functions, tan, hard tan, sigmoid, soft plus, ReLU, and leaky ReLU. So ReLU will squish everything into a value between 0 and 1, I believe. I think a leaky ReLU can actually output some negative values as well. And it looks like they have some more here as well. But I think the most common ones you see are actually the ReLU and the sigmoid. I have seen some tangent hyperbolics used as well, but I've never really used a lot of these other ones. Okay, so here's the figure, 14 by 28. And now he scripts this, which is, it might be a little bit confusing to understand that, but if you look at this, we're making a list of activation functions. So we're saying we want all of these listed, each one. So we have a list of 6. Okay, cool. Now we're going to go through that list, activation function, in enumerate activation list. So we're going to go through each one in the activation list. We're going to put that on a subplot. The length of the activation list, 3i plus 1. We're going to call the title of that the activation function dot name. So that will be the tan, I believe. The output of t is the activation function of the input of t. Okay, so here we're finally plotting our x and y. Our x is the it looks like they both say input. That's kind of weird, huh? Let's plot this and see what's going on. Oh, we didn't actually plot it yet. Yeah, we did. So why is this both input of t? I'm wondering. What's this k here? I don't know why this line of code is here, but I know why this line of code is here. This makes sense. Our x is our input of t, which is our range here, input of t. There it is. That's our x. And our y is going to be red. Oh, okay. I see it. I see it now. Sorry. I know why this line of code is here. So input of t by input of t, that's just a straight line. Okay? So that's why this line is here, this diagonal line. In the red, we have our input by our output, and it's scrolling through each one. Our tan, hard tan, sigmoid, soft plus, ReLU, and leaky ReLU. So we're going through each one and plotting it. And as I said, the ReLU will put us any value in the positive range. The leaky ReLU can give a little bit of negative numbers, so it will penalize those heavier. And these are our nonlinear activation functions. I mean, you can study those as much as you want, as much as you feel is necessary. Now we're going to look at some nodes. So they did this in the book. They show the results of this in the book. So we're setting our A, B, and C to the tangent activation function of various weights and various biases. So a -2 weight, negative 1.25 B, 1.75. So we have an A, B, C, and a D here. And then we're going to add some of them together. So let's just see what the output is here. And let's plot it so we can... Okay, so we plotted it. So we're making another list. Here's A just by itself, B by itself, A plus B, C, D, C plus D. And then we do some cumulative distributions here where we're taking C times A plus B and D times A plus B. And then the most crazy one here at the end. The same type of for loop is used here where we are scrolling through I. We're going through this whole WB list. I guess this line of code here is talking about the subplot. So it's 3 by I plus 1. So it will be like 1, 2, 3, and then skip to the next one. And here we have the same type of plot. This is the black line here. And then the next one is plotted by the input and output, and that'll be listed in red with a line width of 3. And we can see the different ones. So it's all listed at the top. A is this tangent function, so you can see it. They all kind of do similar things. When we take this input, it outputs this. So here's our input in black and our output in red. And if we combine these two, which is what you could consider a node to be doing if it had 2 input values, that's what this output looks like. So C and D, the same thing. So we get kind of you're going to get the same behavior no matter what your weight and bias are. It's going to be a very similar looking thing here every single time, no matter what you change these to. It's never going to be something crazy. But when you add them, you start to get different behaviors. And then when you multiply them and add them, you get even crazier behaviors. So you can see how organizing all these nonlinear functions can give us these different behaviors. Now we're going to go through the actual lesson, which is the neural networks. I don't know if I'm going to go through this part. Maybe in the next video I will. I don't think I'm going to have enough time to hit it. It's just basically showing how you can look at these neural network layouts, and so you can kind of see the hidden layers, the hidden activations, the output layers. So you could run it and see, and then list it in sequence here, named sequence. This is a different one. So we wrote them here. Here we're making our sequential model. Here we're making our subclass model, and then finally named sequence model. Where was that? Named sequence model is here. And then you can just look at the architecture of those, if you will. So not much going on there. We'll figure that out afterward. This is more important, is the beginning of this one. So let's go ahead and restart this code and clear all the output. So we can run this. And here we're getting right back to our temperatures from Celsius, our unknown temperatures, which we know are Fahrenheit. We're going to unsqueeze those in one dimension, and then we'll look at the shape of that. If we didn't unsqueeze it, it would just be a one-dimensional vector. We are unsqueezing it, creating a two-dimensional matrix. TC will have the same shape. Boom. Very good, very good. Let's keep going. So we know what we've done so far. Here's our number of samples. It is the shape of the 0th dimension. The shape, this will be 11. Okay, so we're just grabbing that number. Our validation set is going to be 20% of that, 0.2 times our number of samples. So I think we have 11. I don't know what they're going to get for... Oh, they're making it an integer, so it will round it to the nearest integer, which I think will be 2. We're going to shuffle it. We're going to do a random permutation on that, and then we're going to separate it into our training indices and our validation indices. So here are our training indices: 5, 2, 8, 7, 3, 10, 4, 9, 1. And we have 2 values for our validation indices, which is 6 and 0. We have our validation inval, that just equals 2. Okay, that just equals 2 because we are rounding this number of 0.2 times 11, which 0.2 times 10 is 2. 0.2 times 11 is 2 point something low. It's not going to be over that 0.5, so that's just a rounding thing. We're going to round it back down to 0.2. And here are the shuffled indices listed. So our shuffled indices, we just said, hey, shuffle up these numbers. You got 0 through 10 here, 11 digits, 0 through 10. Shuffle them up. Okay. Now take the first 8 of those shuffled up numbers, and that's our training indices, and then take the last 2, and that's our validation indices. Now we're going to split our T sub U and T sub C into the training set and the validation set. And keep in mind all the while that this is an insanely small data set, right? I mean, we know that we're going to keep working with it. It's what the book chose to use for simplicity, I suppose. But you'll never be working with an 11-digit data set. Now we're going to multiply our T sub U and our T sub U only, and we're going to rescale that as we've done in the past. We're going to rescale this, lower it by 1 order of magnitude. So it's going to be 3.57, 5.57. We're just multiplying by 0.1, just by 0.1. Okay, now let's get to the neural network part of this. We're going to import Torch in as in. In Chapter 5, we did this model. So we kind of created a custom neural network by doing this. That's what we did. A linear neural network, one node. So we're saying make a linear layer of one node. Input is 1 and output is 1. So then we're saying, okay, take our linear model here and look at our T sub U we could do the T sub U and it'll be a larger number, right? We could do the T sub C validation and it's 2 digits. But what if we don't look at our validation? What if we look at our training set? Okay, why are we getting these? These numbers aren't the same as our training set, right? Our T sub C training set is right here. Why are these numbers different? Because when we call this linear layer, it has a random weight associated with it. This is a randomly generated weight. If we rerun it, it's a different randomly generated weight. Every time we call this, it's just randomly generating a number. That's how neural networks are initially populated, is with random weights and biases. We have to train them to become the correct weight and correct bias in order to model the behavior which we wish to model. And that's what we did in the last lesson. We had a weight, and we had a bias. Now we're just doing it using a neural network. All right, so here comes the linear model. So we ran this through our linear model, right? Our T sub U in validation. We could run whatever we want to run through it. We can run an X, a torch of ones. We could run a torch of 12 ones. No, we can't do that. But we can just put this single one value in there. I don't know why we couldn't do 12 ones, because we're running multiple digits here. Oh, I think I know why. If we did 12 and then we said, let's see what our error is. Yeah, we can't do that. We need I think we need to unsqueeze it, right? Just like we did here. And boom. So we had to unsqueeze it that dimension. That's where dimensionality comes into play. If we don't have this unsqueeze here, it says, hey, these don't line up. These dimensions aren't going to work for us. So we add the unsqueeze. We unsqueeze this one dimension, and now we can run it. And we have the same value repeated, because this is just a matrix of 12 ones. If we look at that, it's just, this is what our input and this is our output. So I'm taking a lot of time with this, and we haven't really gotten that far, so I'll keep moving along. Oh, it looks like they did what I just did in this line of code. Sorry. So this is the same thing here, 10 by with an extra dimension, and they're getting the same thing. So I guess this and this are equivalent. Okay. So now let's do a linear model, and now we're also going to define an optimizer. If you remember, SGD is stochastic gradient descent. We're going to define a learning rate as well, 1e to the negative 2. Let's look at our parameters. I don't know what that does for us, but I guess that's just our parameters of the module. This gives us actual data. I mean, maybe this shows us something. I'm not sure what this shows us. But this shows us our data within the linear model. Here's our W. Here's our B. Requires grad equals true. Also going on with this linear model is we have an optimizer defined for it. We'll see that here. Now we're going to define our training loop. Here's our function. It's a training loop. It depends on epochs, optimizer, model, loss function, T sub U train, T sub U val, T sub C train, T sub C val. We're going to go through an epoch, which is a complete iteration of it. So now we're doing a for loop here from 1 to epochs plus 1, number of epochs plus 1. So we'll have to define number of epochs later when we run this. T sub P train is going to be the equivalent of our model of our unknown behavior. So we're modeling the unknown behavior and putting that into our model, and we want our output to be our known T sub P behavior. Our unknown, our known. Now we need to find the loss of that. So our loss of our training data is simply the loss of between these two sets. And T sub P is our predicted. I'm sorry, that's not our known data. T sub P is our predicted. So how far away is our T sub P predicted from our T sub C, our known Celsius? So the difference between these two will give us a loss function, and then we can train with that loss train. And this is our training set. Now we do the same thing with the validation set. T sub P, validation, the loss equals the loss. It's the difference between our predicted and our known. Now these three lines of code are a little different. We're zeroing the gradient every time we do that. So we do this. It's just going to go through this step by step. Now it says, hey, zero the gradient. Okay, now train the loss backward. and then do an optimizer step. So zero the gradient, train the loss. That means adjust your values based on what your loss is, and learn what the loss is, and then do an optimizer step. Optimize each values to correct that loss. And then this is the printing stuff. So we're printing our epoch, what epoch are we on. We're printing our training loss, and we're also going to print our validation loss. Let's run it. Let's define our loss function. Okay, what's our loss function going to be? We have it here. We never see how we never even had to define it. That's because it's in a function. If we tried to run this training loop, it would say, hey, you never defined loss function. So that's fine. Let's define loss function. Very easy. Squared differences. T sub p minus T sub c squared. We're making another linear model here. Optimizer, SGD. And I guess we're saying all of this because, and we're setting our learning rate 1 e to the negative 2. We're defining epochs. Our optimizer equals optimizer. That's here. Our model equals linear model. So if you look at all of these values here, they're right here. Okay, this is our function. We need to define each of these values for our function to go ahead and do it. Our function is a training loop. So it's an iterative process, but it's the same thing. You still need to define it. So a lot of these are just being set to what they're already set to. But number of epochs can be defined every time. Optimizer could be changed. You could take this, Control C, and put it right here. Same difference. And let's run it. All right, your values might not be the same as mine. Why might not think about that? Why would they not be the same as mine? Because this is a random permutation. Okay, so if they're your training set and your validation set, you might have gotten 7 and 10 for your validation set. So these values are, your values here should be pretty similar, because no matter what, it's training on the same data. It should get closer. It might be a little bit different, but it should be close to here. These losses should be similar as well, but they're not going to be the exact same. And ultimately, you want them both to go down. That's the main lesson that I'm trying to hammer down. You want your training loss to go down, and you want your validation loss to go down. In this case, the training set and validation set are so small that you might actually end up in a case where your validation loss is smaller than your training loss. But on a large data set, you shouldn't ever really see that. Your training loss should always be lower, a little bit lower than your validation loss, or around the same. Ideally the same. So let's run the next line of code here. And what are we doing differently here than we did here? Our optimizer is SGD here. Our optimizer is SGD here as well. Stochastic gradient descent. Oh, I see. We explicitly define a loss function here. Here we don't. We're calling it. So here's another shortcut we just learned. All right, this is confusing. It's not. It's not confusing at all. We're just defining a function. It's a very simple 3 lines of code. We can understand that. But we don't need to do that. We can do mean squared error. Mean squared error. I am correct. So you can always just Google a line of code to figure out what's going on with it. And the math might be troubling, but I can assure you it's not that complicated. If we saw it in a different format, it's not doing something super complicated. It's probably pretty similar to the square differences. There's one other thing we're doing different in this line of code, and that is we're setting our number of epochs equal to 3,000. So not as many as 5,000. Not that it matters too much, But from 3,000 to 5,000, we don't see, actually our validation loss is going up. That's not good. That means we actually might be overtraining a little bit, if you remember. Yeah. But not by much. It doesn't like spike up a lot. But that is overtraining. Training loss going down, validation loss going up. This model has been overtrained. In this case, it has also been overtrained. After 2,000 epochs, that's a lot, by the way, it begins to overtrain. Just slightly. Only slightly. So if we did 5,000, I'm sure it would overtrain even more. Yeah, and it begins to go up, just like this other one did. Oh, maybe the mean squared error is the squared difference. I don't know. You'll have to check that. I'm not going to do that during a video, but mean squared error loss, it looks like we're getting the same exact results here. Oh, and another thing is when we train these, we're essentially retraining it. Okay. All right, so linear model parameters, let's look at those again. Here they are here. Here they are here. Here and here. Let's do a sequential. All right, now we're getting into a real neural network. So what we just did a lot over and over again was create neural networks that were the same as the thing we did in chapter 5, which is a linear equation, y equals mx plus b. Now we're going to make it a little more complicated. This is our architecture to our neural network. This is how you see the architecture defined. It's very simple. In sequential. All right, first we want a linear layer, input of 1, output of 13. Then we want a hyperbolic tangent. That's our nonlinear activation function. And then go back into a linear layer and go from 13 to 1. Layer 0. It's a linear. It's got 1 input feature, 13 output features. Then we apply the hyperbolic tangent to all of those. And then we apply a linear layer and subtract it or condense those 13 back to 1. So you could imagine a circle. Where did it show us that? One input, 13, and then it goes through the activation function, so we'd have 13 red circles, and then it goes to another layer, and we have 13 blue circles, and then it would go to this yellow box, our output, if you were going to visualize that. Let's look at the parameter shape. So we're looking at each layer again. We got a 13 by 1, a 13, a 1 to 13, and then a 1. Not too complicated there. So we're seeing it. Weight, bias, weight, bias. Oh, okay. So these are just our parameters. So we're not seeing anything listed here that has to do with our nonlinear activation function. We're seeing layer 0 and layer 2 because those have parameters. If you consider this a layer, sometimes you could consider this as one layer. But let's just say this is a layer, this is a layer, and this is a layer. Layer 0 and layer 2 have 13 weights and 13 biases. And then the inverted of that to reduce it back down to 1 in layer 2. So it takes 1 input and creates 13. It takes 13 inputs and creates 1. All right. So now we're seeing another way to look at our data here. From collections, import ordered dictionary. And then another way to look at our data. This is the same thing we did here, I believe, for name. We look at the different parameters. We're going from 1 to 8, and then 8 to 1. Do they put an activation function? They do put an activation function in here as well. Okay. So now we'll see our bias. Sequential model. That's this here. Why is there only one bias? I guess it's for the final layer. All right, well now we can run this line of code and actually see some stuff happening again. So we're doing an SGD, sequential models. We're setting our learning rate equal to e to the -1. Our model equals sequential model. So this is the one that had 8 layers or 8 nodes. Loss function and MSE loss. We're printing. Oh, so this is during the training. And then at the end, we'll print our sequential model of that. Okay, so this is our output of our validation set. And we'd have to multiply it by 10 to get it back to what we want it to be. And go back up there and compare it to see if it's anywhere close. So it would be 6.7 and 14. Oh man, I don't remember what our validation setting was. So that's fine. That we don't need to go look into that. Hopefully you understand though that we're taking this, our validation set of our unknown, and putting it into our sequential model. That's our output. That's what we get as our output. This was rescaled by 0.1, so to rescale it back, we would have to multiply by 10 and then go figure out what our validation set was up here, which was 6 and 0. Oh, so actually we don't need to rescale it. So 6, this is 0. 1, 2, 3, 4, 5, 6. We should have something close to 0.5 and something close to 3. Close to 0.5, close to 3. Okay? Next, we're printing out the answer. Oh my gosh, I could have just, they do it for me. I'm always checking. I should just read the code before I do stuff like that. So this should be close to 0.5 and close to 3. They're just saying, hey, that was your T sub C validation. Simple way. That's what the answer should be for that. I wonder why they're in inverted order, though. That's a little strange. Huh. It should be 0.5 and then 3, I believe. Yeah, 0.5 and then 3. Oh, it goes 6, then 0. The 6 is before the 0, so it actually should be 3 and 0.5. So that means it's performing a little bit worse than what we want it to. That's probably a result of overfitting, right? So this should be a 3, and it's 0.6, and this should be a 0.5, and it's 1.4. I figured the 0.6 would be associated with the 0.5. All right, and now our hidden. This is our sequential model, hidden linear weight gradient. So this is the W's in our 8 layers. I keep using the wrong word. Our 8 nodes in our first layer. So that's that. Hidden linear. Which one did we call hidden linear? So this is our hidden linear. So what if we said output linear here? Let's see if that prints. That might give us an error. No, it gives us our output linear. So we have 8 nodes here and 8 nodes here. We're just printing out the W's, the weights of each of those here. Whether we do input, and we named our layers. So I guess what we're able to do with this ordered dict is actually name our layers here. So that's cool. Let's go ahead and put hidden layer back in there. I think I did that right. Yeah. Oh, I messed up. Does that work? Alright, I'm not sure what I did. I just hit Control Z to fix it though. I think I deleted weight or something like that. And just did hidden underscore linear dot grad, and it said there's. I think that's what I messed up. All right, now we can plot it. Looks pretty good. We'll go through each of these real quick. This O, I wish I could maximize this somehow. Did I just see an ability to do that? No, I don't know how to make this bigger. Sorry. But the O is the blue circles. So that is just a straight relationship between our Fahrenheit and our Celsius. Our Celsius was the known data. We have this unknown thermometer here, and we're plotting it. And yeah, we could see that it's a linear relationship. If we just plotted those, then we would see that it's a linear. We're like, this is like our first step before we train anything. We can do that. Now let's look at this next thing. So what are we plotting here? We're plotting what our model does, what our neural network does. Sequential model was our neural network. Sequential model. We defined it here. Sequential model. We are feeding in a range here, so I guess we defined this T range right here, 20 to 90. I guess that is it just goes 20, 21, 22, 23. It probably goes in intervals of 1. We unsqueeze it 1 dimension, and we're good to go. We feed that into our sequential model, multiply it by 0.1 to rescale it, and then we have to do detach. I don't know why we have to do detach, and then put it into NumPy. I think we have to do that. We have to do this detach command to get it into a NumPy array. Remember, we're always converting between NumPy and Pytorch, so we're converting this back into a NumPy array. Then this C negative, I guess, makes it be a blue line, and our x-axis is just this tRange dot NumPy. Okay, fair enough. Maybe detach is getting rid of a dimension. Do you want to find out? Remove the set of matched elements. This doesn't look right. I think I've looked at this before. Yeah, let's not get into that. You can figure out what detach once. We're almost done, so I want to finish it up. My video's going very long. This is the best part of the whole thing, because this is what you do when you're trying to model something. When you get a neural network working, that's step 1. That's probably the hardest step. The next step is hyperparameter tuning. So let's run this. And we see a pretty good match here. But I don't think it was supposed to be. I think I already tuned the parameters. I think it started out as like -1 and like 10 neurons here. So let's do that. Oh, it got real screwed up there. It exploded. Wow. If you see these NANs, that means your gradients did not converge. Our learning rate was too large. Let's try -2. Oh, it exploded again almost. But then we said, hey, what about -3? Pretty good. So learning rate obviously makes a big difference. I think we could even go -4. And then we don't converge fast enough, so our learning rate is too small there. So it looks like -3 was the magic number. Does the neurons matter? What if we had like 100 neurons? So that's what it looks like as 100. Let's change it to 2. Oh, not as good, huh? It looks like it's almost overfitting. But it definitely messes up at the end here. So the cool thing about this field is that we can't really say like, hey, if you do 1,000 neurons, it's way better. Or do 100 neurons, it's way better. Like there's no explicit laws. There's ways to help figure it out, but like even that, it doesn't look as good. So you just want a good model at the end of the day. So you need to tune these hyperparameters. So there's a lot of different hyperparameters in here. Here we have a tan. What was the different activation function we had? How about a sigmoid? And here's our neuron count. We'll do less than that. We'll do 10. We'll throw in a sigmoid. Could I just type in atom? Yeah. And then we get that. So I tuned even more hyperparameters, right? I could tune the number of epochs. I can tune the learning rate. I can make this learning rate larger again. I think what did I do? There we go. Still going down. Atom can handle the higher learning rates. If it's not Atom and it's SGD, it won't handle it. So this is called playing, and this is when you learn the most. Oh, it actually did handle it. But the validation loss is spiking. It is overfitting in a way. I thought it didn't handle it the first time. Oh, because we didn't have that. We had a tan. And then this one doesn't work, right? So you can kind of see how different stuff works and different stuff doesn't. And this is kind of what you end up doing when you're actually modeling stuff, is changing the hyperparameters. Not always having, hey, I know exactly how hyperbolic tangent works, or I know the ins and outs of the atom optimizer function. You don't necessarily need to know all of that, but you need to know how to implement it. And you need to know how to debug your code. But that is it. Thank you for watching. That's the end of the stream. That's all of Chapter 6 in one shot. So I think we'll do a few more chapters, and that will be that. Thank you very much for watching.